Today I'm going to answer the question, what is general relativity? So before I even begin to answer this question, why don't you ask yourself that why are you even here? So what is something that attracts you to general relativity? Well, few of too many reasons for which at least I am a big fan of general relativity are as follows. So general relativity, well, first of all, general relativity is one of the few brand new subjects. So it's one of the few brand new subjects that students see late in the game, that is after they have a pretty solid understanding of the basic physics, right? And so that's just one of the reasons. Let me mention a few more and then we will get back to our main question. So also that general relativity raises and addresses some of the big questions in physics. For example, in cosmology, and questions like what even is the nature of space and time, or space-time, right? And well, another point that I would like to mention over here is that general relativity is half of the most perplexing issue confronting theoretical physics. So if you take a guess, what would that be? Well, it's quantum gravity, right? So quantum gravity. So GR is half of the most perplexing issue that is confronting theoretical physics, which is this quantum gravity, right? Okay, so these are only the points that I would like to mention, that why at least I find general relativity very fascinating. And you could think of a lot more and you could come up with your ideas or points that you find general relativity amusing. Okay, so again, now before I get to the question that what is general relativity, another very important question that actually needs to be answered is what is so general about general relativity, and how is it related to SR? So how is general relativity related to SR, right? SR being special relativity, right? Now, a lot of people actually think that general relativity is the generalization of special relativity. However, and let me say this, that they are absolutely wrong, right? But come on, who could really blame them, right? With the name convention, or it's general relativity, special relativity. I mean, it does make you think that it would be the generalization of special relativity, right? But yeah, it's not. So general relativity is not the generalization of special relativity, okay? So now that we have this very important thing out of the way, let's come back to the question that is, what is so general about general relativity and how is it related to SR, right? Okay, so to answer this question, right, we will need to consider familiar correspondence principles. Now, I have talked about these correspondence principles in much more depth than I will in this video in one of my previous lectures that was on the frameworks for physics, right? Okay, but being nice enough, I'm quickly going to go through. Yeah, so I'll quickly go through some of these. Actually, I'll quickly go through all of these correspondence principles, right? But then again, of course, if you want to know about these in depth, then I would suggest that you should go and watch that video on frameworks for physics. In fact, most of the things that I'm going to do from this point on would be from that video. However, I will, of course, be mentioning some new points in this one, right? Okay. So, yeah, the first one, and in fact, the most limited framework is of the Newtonian mechanics, right? And then again, these are the frameworks for mechanics. Okay. So, actually, let me do it this way, right? So I'm going to draw some funny looking diagram, right? And I'm going to say Newtonian mechanics as NM. So this one is Newtonian mechanics, and it is the most limited framework, right? Now, we have another one that is special relativity, and let me just write it over here. So SR for special relativity. Now, the correspondence between Newtonian mechanics and special relativity, so that means if you have to go from special relativity and you want to be able to get away with using Newtonian mechanics, what you need is that the speeds that you're calculating are much, much smaller than c. And now we have another one, the other framework, that is of non-relativistic quantum mechanics, right? So QM for quantum mechanics. And then the correspondence to a Newtonian mechanics would be, in terms of path integral, we have this action in this path integral. And if the action is much, much greater than h bar, in that case, you can get away with using Newtonian mechanics, right? Okay, now we have talked about speeds that are very fast. We have talked about things that are smaller. We can then talk about things that are both small and very, very fast. So that is in quantum field theory. Now this is also a framework, don't let the name confuse you, quantum field theory. I have mentioned in the previous video that was on frameworks for doing physics. In that video, I have already mentioned that how a framework is different from a theory, right? So a theory is basically a combination of a framework and the degrees of freedom and their interactions. So when you combine these two, that's when you get a theory, right? Okay. Now, the correspondence between QFT and quantum mechanics would be, again, if your speeds are much, much smaller than the speed of light, right? And that's when you could get away with using quantum mechanics. Okay, and the correspondence to special relativity would be that if you have your action is much, much greater than h bar, so that's when you can get away with using special relativity, right? And then eventually you could garter for these two conditions and you could get away with Newtonian mechanics, right? But then again, Newtonian mechanics is a very, very limited framework of all of these, right? Okay, so now in all of this, you don't see general relativity, right? In this diagram, there is no general relativity. So the question is then, where does general relativity fit in? Well, all of these over here, QFT, Newtonian mechanics, SR, and quantum mechanics are all frameworks for mechanics. And then by themselves, of course, they then do not constitute any theories. And again, like I have mentioned just now, to have a theory, you need a framework plus the degrees of freedom and their interactions. So the punchline over here is that general relativity, GR, is a theory. It is not a framework, but in fact it is a theory. Now, what is it a theory of then? That's the question, right? Well, it should be almost obvious to you that it is a theory of gravitational interaction. So it's a theory of gravity, right? Now, saying this has two particular conclusions, and the first one of which is there is no correspondence principle that is going to relate GR with SR, right? Because GR is not a framework, so there is no concept of this correspondence principle that would relate the two, right? General relativity and special relativity. And point number two, or the conclusion number two, would be that general relativity is actually the generalization of Newtonian gravity, right? So GR, it is not the generalization of special relativity, but it is the generalization of Newtonian gravity. Newtonian gravity. Right. And it is needed when the ratio of mass to radius of a body is greater than or equal to c squared over g, where c is the speed of light, right? And g is the universal gravitational constant. Okay. Now, by this, everything that I have done over here now, I have answered the question for you, what is general relativity? So I have also answered that what it is not. So it is not the generalization of special relativity, and there is no correspondence between general relativity and special relativity, and it is not a framework. So general relativity is not a framework, but what it is that GR is the generalization of Newtonian gravity, right? And it is a theory. Okay, but with all of this now, you might still ask me that, well, how is GR and SR related to each other, right? And the answer to this is simply that SR is just one particular solution of general relativity, right? So let me actually, in fact, write this down over here, that SR is a solution to general relativity, right? Just one particular solution of general relativity. That is when we have a flat space-time a flat space-time with no gravity acting on it, right? So with no gravity acting, right? And that's what SR is, right? So it's a solution to general relativity, a flat space-time with no gravity in the picture. Okay, now I could end this video over here, but where's the fun in that, right? What we can do more in this lecture is actually to go ahead and paraphrase general relativity by analogy with another theory which you know well, right? And that is the theory of electrodynamics, right? So again, what I'm going to do from here is I'm going to paraphrase general relativity by an analogy with electrodynamics, right? And here you will get even more in-depth idea of general relativity. So in electrodynamics, what we have is a set of 4 equations, right? That's where we usually start electrodynamics with. A set of 4 equations that are gradient of E. Assume the vector symbols, right? So I'm not going to write the vector symbols now. So we have gradient of E is rho over epsilon. We have the curl of magnetic field, which is mu naught current density, which is a vector, plus mu naught epsilon naught partial time derivative of the electric field, right? And these 2 equations, they have a name and they are called field equations. Field equations, right? And then we have 2 more, which are the curl of E, which is equal to negative partial time derivative of the magnetic field, and we have the gradient of the magnetic field vanishes, right? And these 2 equations, they are called the Bianchi identity, right? And so I'm spelling identity wrong. Yeah, by Bianchi identity. And these Bianchi identity equations, they come from the geometry of electromagnetism, right? Okay, and then all of them together, they're known as what you call the Maxwell's equations, right? Okay, now the question could be that, or let me ask this from you, what do Maxwell's equation tell you, right? So you have studied them, right, in depth indeed. If someone comes to you and they asks you, what does Maxwell's equations tell you? What would you tell them, right? So here's what I would tell them, that Maxwell's equations tells you how the sources rho and current density J create the fields that are electromagnetic field, that is electric field and magnetic field, with some topological constraints, right? And that's what Maxwell's equations are telling you. Now, all of this that I have just written over here is only half of the electromagnetism. The other half lies in a set of 2 equations, and they are, let me write them over here now. The first one is the Lorentz Force, right, which is F E M which is equal to the charge Q times the sum of electric field plus V cross B, right? And let me just get rid of these vector signs. Even though they look really beautiful, they take time, and somewhere I might forget them, and somewhere I will remember to put them on, and then you'll get confused, right? So if you're watching this video, I hope that you know what vectors are, right? Okay, or what vector quantities are, and how do you represent them. Okay, now this one is the Lorentz Force law, and I said two equations. So the other one is the famous Newton's second law, right? So that is sum over I Fi B is equal to M B A B, right? And this is Newton's second law, right? Now, the question would be, what do these two equations tell you? The Lorentz Force law and the Newton's second law, right? And we use the Newton's second law to understand the dynamics of the system, right? And the Lorentz Force law is giving us the force that is acting on our objects, right? So the question is then, what do these two tell you? Well, these two will tell you how particles are going to react to a field, right? Okay, so you could take, for an example, say you have a hydrogen atom, right? And a hydrogen atom consists of this proton and an electron. Well, it consists of a nucleus, but neutrons are not charged, right? So I'm just going to say proton. And the electron is in this vicinity, right? So there's a cloud of electron, and there's only one electron. So you could solve for this proton as the field, the electromagnetic field that is produced by this proton. And once you do that, once you get the field from this proton, you can simply ignore the proton, put it out of the picture, and just consider this field, and then you can put in things that are test particles. We could say we could put in this electron in this field, and then you could see with these Lorentz Force law and Newton's second law that how does this electron behave in this field that was created by the proton. And as physicists, we often do this. We set up a background for us that was in this example as this proton field, and then we put in things over there. In this example, we put an electron in this field, and we then solve these equations to understand, right? Now, similarly, in general relativity, what we have is, let me first write this heading, general relativity. So far we had been talking about electrodynamics, right? And we were going to make an analogy, right, of general relativity to electrodynamics. And it is sort of similar, but in general relativity, the equations that we have are, first one, that is, you could say, corresponding to the Maxwell's equations in electrodynamics. What we have in general relativity is the Einstein's equations, right? Now, well, there is only one equation, but it has a lot of components, right? And so you could consider them as equations. Now, Einstein's equations, they tell how the sources create gravitational fields or curvature. So actually, let me even write this down. So they tell you how the sources creates gravitational field or curvature in space-time, right? And then corresponding to these two equations, right, the Lorentz Force law and the Newton's second law, so the equations that tell you the dynamics, right, corresponding to that, what we have in general relativity is actually a very beautiful equation, and that's called a geodesic equation. And this equation, the geodesic equation, is the one that is going to give you all those bizarre results, right? That is the beginning of time, the Big Bang, and the black holes, wormholes, and all of those astonishing and mind-blowing solutions to the Einstein's equation, right? And so that's why we first have to be very comfortable and believe in the Einstein's equations. And then when we solve the geodesic equation and when we get these results, then we have to say that they are true. And well, we have a picture of a black hole as well. So one of the results of the geodesic equation is the black hole. And so then what does the geodesic equation tell you? It tells you how a test particle responds to the curvature that was created in space-time. So tells you how a test particle responds to the curvature in space-time. Right? Okay. Now, I have said everything that I could have said for this video, but there's one point that I would still like to mention over here is that in general relativity, right, we don't have a gravitational field. Now, you might be like, wait, what? Well, a gravitational field in Newtonian sense, right? We don't have that kind of a gravitational field. However, in describing the curvature of space-time, we are going to need to introduce the single most important element of GR, general relativity, and that is going to be the metric field, right? And then of course now this is not a video on the course general relativity, but it's just a video that I like to put out there for people who are wondering what even is general relativity. And then I hope that this clears up a lot of misconceptions that you might be having, which I mentioned in this video, that what general relativity is not. In fact, you would even have most of your instructors, teachers even telling you that general relativity is just a generalization of special relativity. And as I have demonstrated or showed you in this video, that is not true, right? It is just a generalization of Newtonian's gravity. That's where Einstein started himself. He was generalizing Newtonian's gravity. That's what he had in mind. He pictured Newtonian's gravity, right? And not special relativity. And special relativity is actually one of the results of general relativity. So I hope this video gives you a very beautiful insight to this beautiful subject of general relativity. And that's all.